In this video, I'll walk through the process of training my first simple policy, with the target of balancing the bipedal legs. I'll use the deep deterministic policy gradient algorithm, with a few tweaks. This first policy is really like an initial prototype, just to check that I'm getting the basics of the algorithm right. In subsequent videos, I will slowly extend the scope. So first up, what is this policy gradient algorithm? Well, it's an online algorithm, in that it combines the data collection, together with the process of actually training the models in some continuous cycle. The basic idea is as follows. We have the legs in some state, and an initial policy. The policy allows us to calculate the next actions to be taken. These get applied to the legs and they move to the next state. For the new state, we can calculate the reward, which is a measure of how good the state is from the perspective of balancing. Now these data points get aggregated into our data set and kicks off a training iteration. For training, a batch of data is grabbed from the dataset and used to firstly update the action value function. Remember, the action value function maps from state and action to the future reward. This updated function is then used to update the policy model. And the overall cycle continues. With the updated policy, a new set of data is collected and used to update the models. Which is great, but unfortunately with the legs, this online approach is not really feasible. We don't have the compute power, and there's a high probability the initial policies could end up trashing the legs. An offline algorithm appears to be much more suitable. The idea with offline is that a whole bunch of training data would be collected in one go, using the same fixed policy. This generates the dataset that's used to train the action value function and the policy. Unfortunately, it seems that this offline approach doesn't tend to work too well. So what I ended up trying here was kind of a combination of the two. Firstly, collecting a big chunk of training data with a fixed policy, and adding this into the dataset. Then switching to the training side, and learning the action value and policy mappings. So far, so good. Same as the offline method. But rather than stopping the process here, I continued the cycle. The new policy was used to generate another set of training data, which gets added to the dataset, and a new set of action value and policy mappings are trained. It's similar to the dagger process that I went through before with behavior cloning, except for not having to tweak the labels. So this was the chosen approach for implementing the policy gradient algorithm. Now let's look at the details of the various steps in this online-offline algorithm. Firstly, with the legs hardware. The plan is to start off cautiously. So the knee joint will be held at a fixed position, at a value that's fairly low. This means that the legs are actually stable on their own, thanks to the curved feet. And for balancing, only the hip joints will be used. Both hips move together using a single control signal, so that the torso can rotate forwards and backwards to try and keep things balanced. Next step, the actions. When taking the actions and collecting the training data, it's important that the system can go exploring outside the scope of the current control policy. So when grabbing the training data, several sources of noise are injected. For the incoming pitch set point, random step changes are added. And on the control actions sent to the hips, low-pass filtered Gaussian noise is added. as well as some random step changes. Now at low knee heights, this works pretty well. The curved feet help make the legs stable, and they happily go exploring. In future videos, the plan is to try and increase the knee height and see if the trained policy can cross over into the unstable region and continue to balance the legs. So next step, looking a bit more closely at the reward. To calculate the reward, we're using the error between the actual torso angle and a set point. Then to get a suitable, kind of bell-shaped curve, the log of the squared error is taken. I have no real idea if this is a good definition for the reward. It's simply a starting point. Now, in reinforcement learning, a slightly more generic metric is normally used for training the policy, something called the return. The return is basically the reward for the next state, plus a weighted or discounted sum of future rewards. Now, moving on to the action value function. This was actually the most difficult part of the algorithm to get working. There are many design decisions and parameters to be set. So I had to work through in steps, solving first a more simple problem, and slowly adding back the complexities. Just to recap, the action value function learns the mapping from state and action to a future return value. The return value is defined as the discounted sum of future rewards, which can actually be presented in a recursive form using the reward value plus the discounted future return. There's a one-step version and an n-step version. Also, in the policy gradient algorithm, they introduce the concept of target networks to help with stability. So in these recursive equations, the target return is actually used. Now, as I said, I tackled the action value function in steps and made many of the design decisions just through training a standalone action value function. So firstly, let's wind back the return to use the Monte Carlo version, which is calculated directly from the training data. This turns the training problem into a more simple supervised learning problem. So I can play around with the underlying deep learning questions, like what model types, structure, sizes, data sources, which was kind of a mini project in itself. After much trial and error with different models, parameters, I eventually settled with a recurrent encoder-decoder type model, with all of the input signals coming directly from the training data, and the output being the calculated future return values. In terms of the state and action, the state consists of the set point, IMU, and servo position data, and the action being the next control value sent to the servos. The model is only looking one step ahead, so it only needs to estimate the next return value. As I said, this was initially worked through with the Monte Carlo return values, and then validated with the one-step and n-step recursive models using the target returns. And one final sanity check to see how the estimated return values vary with action. The curves typically had a single maximum that mostly lay within the valid range of actions, which was somewhat comforting. Continuing with the algorithm, the next step was to look at the policy. The policy provides the mapping from state to the next action. I went with a model that was very similar to the action value function, an encoder-decoder model. All of the inputs to the model, the state, come from the collected training data. The policy tries to estimate the next action, the next single time-step action to take. So that's all of the models used in training. Now the final step in the process is to connect the trained policy and the inference policy and close the loop. Unfortunately, this requires a little bit more work. When training the policy model, we get a mapping from the current state to the next time step action to be taken. However, when we run the policy to perform inference on the Raspberry Pi, we need a slightly different model. For inference, we need to be able to map from state to a time sequence of future actions to be performed. This is due to the limited compute capability on the Raspberry Pi. It can't keep up with the timing needed to perform one step of inference for every single time step. This problem is quite easy to solve. The trained policy can be used to run through the existing set of training data and add its predicted single-step actions to the training data. This updated training data can then be used to train the desired multi-step policy, basically using supervised learning. So that's it, full circle. That's the process I went through for training with the policy gradient algorithm. So how did it go on this somewhat simplified initial task? My thoughts? It seems to have learnt a policy that is somewhat stable, at least when poked a few times with a stick. The behaviour seems reasonable. If you slow things down a little, it does seem that the policy is trying to keep the torso at some fixed angle, which I think is a pretty good start, given that's how the reward function is defined. So at least the algorithm appears to be working as planned. How will this go in the future as the scope is slowly increased? I'm not too sure. In the next video, I'll start trying to increase the knee height and see how things go.